March 5th, 2016. I was watching a documentary on Albert Einstein. It says, Albert Einstein, How I See the World. I'll link this to the bottom. But a few thoughts came to my mind. I was taking notes as I was watching it for the first part of the movie, or first part of the documentary. And I noticed a few differences. Now, I want to point these differences out because the way people go through life as scientists and doing things, and the way I've experienced how things actually happen are completely different. Einstein was more of an intuitive type person. He never really looked at experiments or demonstrations. It was mostly in his head with math. And I know some downfalls to having things mostly just in your head. You kind of become detached from reality. You have to sort of connect reality to your intuition. And you do that with experimentation and demonstration. But there's two differences between demonstration and experimentation that I've noticed. Experimentation kind of like puts your mind into a box. This is by the book, everything has to be just so, and then you lead to the conclusions, and then that's that. With demonstration, you can go willy-nilly and do whatever. You're not really looking to take measurements. You're not looking to make things by the book. You're looking to just say, wow, what's going to happen? You know? And that's what I do a lot of. I mix, whoa, what's going to happen with my intuition. I think that's very valuable to do. I suggest if anybody wants to do demonstrations, don't worry about trying to take measurements of things and just kind of get a feel for what's happening. And I think that's one of the big differences between me and people that are like Einstein, the mathematicians and things. They're inside their heads. They don't really make the connection they need to with reality. And that being said, what I was doing over the past month or two, I don't think I showed you guys this stuff yet, but I went to work and I grabbed a whole bunch of copper wire and I was like, check this out. I put it into my little crucible and I melted it into a giant chunk of copper. I mean, that thing was freaking hot, man, when I was melting it down. Well, this is like the end result, because I had blown up the crucible. I had it really hot, and I decided to take the hose and at a distance shoot the hose at the crucible, and it exploded from the flash steam. But it was really interesting. I think I should post some videos of me doing the crucible thing again. But anyways, look at that. Look how crazy that is. And when I had the crucible going good, I was just pouring the liquid copper on the ground and just, you know, playing around with it, just doing things willy-nilly. And the reason why I say this is because Einstein was more of a special relativity, time and space are interrelated. That's good. Special relativity is good. General relativity is nonsense. It's pseudoscience. But special relativity is good, sound reasoning. I like special relativity. But there was no experimentation and demonstration involved in it. You know, it's not something you really need to. It's like a big picture kind of thing. But as well, stellar metamorphosis is actually also really big picture too. It has to do with the actual physical stars. Now, the reason why I was melting down metal is because I want to understand how much heat was involved with melting down metal. What would you have to do to make sure that you could get a big liquid soup of white hot metal into a big ball in outer space? And I found out that you need to be able to block the heat loss with refractory material, which is the outside concrete of the crucible. And you had the crucible inside, which was, you know, a salt and half propane tank kind of thing. Of course, I had emptied it out before I salt and half and wanted to explode on me. But anyways, I did that. And you also need to have like lots of air. You need forced air in there, and you need fuel. You need the charcoal. I was using charcoal for this. I don't know if you can still see little bits of charcoal in there, but it's lots of charcoal hanging out in there. But you need a lot of things to melt down metal, and I wanted to do that demonstration because it became real to me. If you're gonna have iron and nickel in outer space forming into giant, massive, like pure asteroids, and you have nothing to block the heat loss, and you have nothing to force air in there, you have no fuel to melt it. How exactly does that happen? Well, you needed to have something to provide the heat loss from happening. You needed something to encapsulate all the material, and you needed a direction for it to all fall down into. In essence, the crucible, the liquid metal would fall down to the bottom. And in our space, you don't really have that. You don't have that. And I thought to myself, well, you need to have something that's really, 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 really big and hot to make something as massive as the Earth and the core of the Earth. And even Mercury. Mercury's core is the same size as Earth's core, yet Mercury's a lot smaller because a lot of the outer layers have been ripped away. But how do you make an iron nickel ball that massive? It just doesn't stick together because of gravity. That's ridiculous. You take copper wire and you just stick it on the ground and gravity melts it down? No way, no way. You had to have something as massive as a star to create something as big as the Earth, because that's what happens inside of it. It's a giant refractory, like, chemical experiment kind of thing where it just takes all the interstellar material and just collects it in the center and makes a giant ball out of it, That's what happens. It's a big picture thing. Also, it can be understood intuitively, but I wanted to do a demonstration on it to make sure I knew what the basic fundamental principles were of this. And that's something that the scientists these days, they seem to skip over. They don't understand that in order to manipulate physical matter, you need to have physical principles. You just can't throw math equations at it and expect yourself to understand. There's no comprehension in math equations. You need physical reality. As well, another note I wanted to make here, something I saw, this is a little off tangent here, is that I was always thinking, before I made the discovery of what Earth is, what happens to stars as they cool, collapse, become hard, rocky balls of differentiated matter. Before I realized that, I was always searching after a specific question. One thing was on my mind. I was always thinking about. And that's another thing I had similar with Einstein, is that he was always looking at, okay, well, what would it be like if I was riding on a motorcycle traveling near the speed of light? What would the world look like as I passed by? And he answered with special relativity. And with me, mine was always, why should something really big cause it to pull? Gravitation. Why should the Earth being really big cause it to pull something? Why should the sun being really big cause it to pull something? There was a disconnect there. Having something really big does not cause it to pull on something. What's happened in science now is that these scientists, they've accepted Einstein's general relativity as being sound because of special relativity being so incredible. But general relativity is nonsense. Something being really big doesn't cause it to pull. That's correlation. They found a correlation between mass and gravitation. The causality of it is not mass. Mass doesn't pull on things. Mass is mass. Gravitation can be caused by something being heavy. That doesn't make any sense. That's a correlational thing. What you have here is you have a missing variable. There's something causing the mass, and it also causes the gravitation. We have a missing piece of the puzzle here, and to really get the word out there is very important. But that alone is what I realized, and obviously discovering what the Earth is when I was trying to figure out what happens to stars. Then I made the discovery, but that was my main question. And I think it's good for scientists to really focus on one specific mystery, because you never know where that's going to take you. But as long as you can keep yourself focused and just don't go all over the place with all these other random things, keep focused on one specific question throughout your entire developmental career, between development, your entire development. Always keep in a specific track of things, and then you can let your mind branch off wherever it wants to go naturally. But as long as you give yourself some type of road to stay on as you progress, I think that's the best option, because that's what Einstein did, and that's what I did. And I think a lot of other scientists do that as well. Just keep your mind focused. And you never know what's going to happen, you know? Keep your mind like a laser beam, and you never know what you're going to discover. But anyways, so yeah, I wanted to show you guys this too. I had scored some titanium. Check that out. Isn't that cool? Sounds weird. It's a little titanium rod. Hopefully I can get a hold of some Inconel too. And Inconel is a nickel super alloy. Yeah, that's something gonna be really cool. But I have, you know, silver, gold, copper, you know, all that good stuff. But turning out that I like to collect all this stuff and, you know, see what it feels like and see how it behaves and what it sounds like and stuff. I think I'm gonna get a hold of a meteorite. Maybe I'll buy like a little cheap little piece of something that's polished. But anyways, hopefully, you know, this helps people understand there are differences that exist as you study these scientists, as you look at their history and who they are as people. There are lots of differences, and if you can point those differences and take the good and leave the bad, I think you'll be better off.